In this problem, we have a linearly increasing load density, that is a force that is spread out linearly over 6 meters of a beam. We're asked to find the magnitude of the total load as well as its location as it would be experienced in the centroid. We're supposed to find where the total load centroid is, and that's for part A. We'll use the following strategy. First, we're going to write a function, f of x, that defines the applied load over the span of x. So we're going to find the equation of this line here, this load, increasing load line. Next, we're going to use that function of load over x to find the total load by integrating over x. Breaking that down, we're looking for the force of the total load. To do that, symbolically, we can represent that as the integral from the 0 to the length of the beam, which is 6 meters, integrated over the differential of F, the differential force load. And since we've written an expression of the force density, this F of x, we can integrate that force density over dx to get the total load F of t. Finally, we'll also use that function of load density F of x to determine the centroid. And in determination of that centroid, we'll also use the total load that we found in the previous step. But symbolically, that's represented as the integral of the product of x and differential force load density over the total load. And breaking this expression down further symbolically, this differential load density we can express as f of x times dx, the infinitesimal over the span of the beam. So, well, let's get started with step 1 here. F of x, we first can find the slope. The endpoint is 1600. The starting point is 400, and that's over a span of 6 meters. We can write that as follows. And I'm going to write these in a somewhat odd unit of hectonewtons for meters divided by the total span of 6 meters. That's going to be our slope, and since we're writing the equation of a line, it's the slope times the variable, in this case x, plus the offset. And since we see that this is not originating at 0, but rather at 400 newtons per meter, we can write this as plus 4 hectonewtons per meter. And that is our force load density equation, f of x. Next step, we're going to integrate this force load density over the beam length. The beam spans from 0 to 6 meters. So we can break this down. 16 minus 4 is 12, divided by 6 is 2x, plus 4, and I am omitting the units here for mathematical clarity. We'll put them back in after we're done the integration. We do the integration term by term here. The integral of 2x dx is x squared over 2, so the 2's cancel. We're left with x squared. The integral of 4 dx is 4x, and we're going to evaluate these from 0 to 6. That becomes 60 hectonewtons. Okay, That is the magnitude of our force. Technically, we want to keep track of its direction as well. We're showing that all the force vectors in the load are pointed downward. So, integrating, summing all those together, the result will be a downward vector. So, we will correctly represent this total load as, and we'll put it back into a normal unit here, 6,000 newtons in the downward direction. Okay, so we now have our total load force. But all we know is that it's pointing downward. We don't know where this force could be concentrated along the beam. That we'll do our next step. In step 2, we'll find the centroid. So, I'm sorry, in step 3. To find the centroid, we will use that force load density function that we defined, but this time we're going to integrate that by the product of x over the span of dx. So this is going to turn out to be a different integral in the numerator. Our denominator is simply the total load, which we determined in the previous step, step 2. We will show the product of x, f of x, which comes to 2x squared plus 4x. Integrating that, we are left with 2/3 x to the third plus 2x squared that we evaluate from 0 to 6. And all of this is over our total force load magnitude of 60 hectonewtons. Plugging in the numbers here, the 0, fortunately, we only have to concern ourselves with the upper boundary, which is 6. The 0 for the lower boundary equates to 0 since all of these have x variables. And this can be written as 36 times 4 plus 2 hectonewton meters divided by the total load of 60 hectonewtons. That turns out to be 3.6 meters for the centroid of the total load. Okay, that concludes our answers for part A. Now move on to part B. Now, given what we know about the load forces, we're asked to find the reaction forces of the beam support at point A. Since this is a static system, we know that all the linear forces, both the load forces as well as the support forces, must sum to 0. We also, so it's moving nowhere, it's staying put in space. It has no translation in any direction. It's staying in the same location, and that's what these linear forces mean. The other way that an object can be moving in space is rotating about some point. So since that's not the case here, all of the torques, the load torques, as well as the support torques must sum to 0. So summing up that explanation, the reaction forces and torques exactly oppose the load forces and torques in a static system. So that makes figuring out the support forces or the reaction forces of at the supports fairly easy, since we already know our total load forces, and we know that our reaction forces have to exactly oppose them. We knew that the magnitude of our total load force was 6,000 newtons, but it was pointed downward. So our reaction forces have to exactly oppose those. So it will point upward. Actually, let's be strict here and write out inequality. And it is a vector. Let's box that. Secondly, we need to find, since our system is not rotating, and there is a total load about the with some moment about the support. So there's a torque exerted on our support. Since we know that the torques must also cancel, there is an exerted torque at support A that must exactly oppose the torque occurring about the centroid. So it must be exactly opposite that that occurs at the centroid. So we can figure out the magnitude of this torque by multiplying the location of the centroid at 3.6 meters times the total load. And we know that the torque is exerted in the clockwise direction by the load. So the reaction forces have to oppose that exactly, so they'll be the same magnitude in the counterclockwise direction. And that can be written as, using this book's notation for torque, I believe, 21.6 kilonewtons meters. Let's do that better. Sorry, guys. .6 kilonewton meters. CCW for counterclockwise. And that concludes our problem.